Okay, welcome to the Unit 1, Lesson 5 video on graphs of absolute value functions. In this video, we're going to explore how to graph an absolute value function on a coordinate plane, and we're going to look at some different types of transformations to change those graphs, different aspects that can move the graph around on the coordinate plane. So before we do that, we're going to take a look at the parent function. The parent function is just a very generalized form of the absolute value equation, and it looks like this: f of x equals the absolute value of x. So again, just a very simple equation that's not a lot happening. So if I want to look at the graph of this, I can draw it using a table of values. So just start with that. So say x and f of x, which is really just y. And now I'm allowed to just pick any x values I want. So I'm just going to pick some nice simple ones: -2, -1, 0, 1, and 2. And then I'm going to take the x values and plug them into my function and see what happens. How do I get my y? So we'll start with f of -2. That would equal the absolute value of -2. And that would give me 2. Now I just plug in my next x value of -1. And that would give me a y value of 1. And I just continue through here, plugging in my x's and evaluating, getting y values. Now we're not going to continue doing this. This is what's nice about graphing with transformations, is we can actually do this in a much simpler, faster manner. But since we don't know quite yet how to do that, we got to do it the long, tedious way. So I now have a set of points here, and I can take those points and graph them on the coordinate plane. So here's -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. So I can now use those points to kind of sketch the graph and realize what's happening here. Okay, so here's my graph of the absolute value function. So a couple things I want to show you here. The first is just that there's some symmetry going on, right? You can see this here, that the graph kind of, if I was to fold this over the y-axis, these points would sit on top of each other, right? You can add this point here, and this point here would be the same. This point here and this point here would be the same. That's the axis of symmetry. And you might have heard this term before with quadratics. It's basically the same thing. It's the axis of symmetry. It's the line in which divides it in half. The other thing I want to talk about is the vertex here. That's the point where it changes direction. Right? So when we talk about the vertex, the point at which it changes direction, because it's such an important point for graphing with transformations, we're going to give it some special notation here. We're going to call it h, comma, k. So h represents the x value of the vertex, and k represents the y value of the vertex. The next thing I kind of want to talk about for these absolute value functions, just kind of notice that this is really just a line, right? It has a constant change, right? Up 1 over 1, up 1 over 1. And I can just keep following that and get into new points. Except on the other side, it goes up 1, backwards 1, up 1, backwards 1. So it's really the same consistent slope of a normal line. And that's what's nice about an absolute value. If the x is to the first degree, then this is basically just a line. From the vertex to the right, you can graph it like a line. And that's going to be very important and helpful for when we graph our lines. So let's start to take a look about the different types of transformations that we can make. The first transformation we're going to talk about are reflections. All right? So we can have a reflection where the negative sign is in front of the absolute value, right? It's on the outside, which will cause it to flip over the x-axis. Or the negative could be on the inside, which would cause it to flip over the y-axis. Now we're not going to look too much at these types of functions where it's reflecting over the y-axis. It's going to be important for later math classes such as pre-calculus or calculus, but for Algebra 2, we're not going to mess around too much with this. We are going to focus on this reflection where you're reflecting over the x-axis. So what that would look like if I had a coordinate plane here, and here's my parent function. If I was to reflect it, right, then it would look like that, where the points literally just come from being positive y's to negative y's, positive y's to negative y's, and that's just a reflection over the x-axis. All right. The second type of transformation we're going to make are stretches and compressions. And that all has to do with the number that's outside in the front that's being multiplied. So a vertical stretch or a vertical compression is all about multiplying the absolute value. So because it's a multiplier, we can either compress or stretch depending on if that number is less than 0 or if that number is greater than 0. So we have absolute value here and here because it doesn't matter what the sign is. If the sign is negative, that's a reflection. If it's a positive, then it's not reflected at all. So that's why we put the absolute value here when we talk about stretch and compression, because we don't care for a stretch or compression if it's a positive multiplier or a negative multiplier. It's all about the number itself, the value of the number. So less than 0. Actually, that should be less than 1 or greater than 1, right? Because less than 1 is a fraction, right? When you multiply by a fraction, you're going to compress, right? The values will get closer to each other. If you were to multiply by a number greater than 1, then it's going to get farther away. Your y values will grow larger. Okay, so as you can see, I've added these real quick graphs to show you the difference between if it's a compression, because a is less than 1, or a stretch if a is greater than 1, and what that would look like. So again, the parent function would be here at 1, 1, 2, 2, 3, 3. Right? So here's my parent function. If I stretch this by a factor of 2, then that's really, the slope would be 2 over 1. So this would go up 2 over 1. So you see that y value of 1 is multiplied by 2 to get you to 2. And if I did that again, up 2 over 1, I'm now here at 2, 4. So that y value of 2 was multiplied by 2 to give you a y value of 4. And then that could reflect over here. And you see how this now is going up at a much faster rate. It's been stretched upwards. Whereas if my compression, right, is 1/2, instead of going 1, 1, 2, 2, 3, 3, and backwards the same, then I would go up 1 over 2, and that would have a point here. Or if I go up 1 over 2 again, it'll be here. So instead of a y value of 2, it's now a y value of 1, because it's now half as tall. And that would exist also over here on the other side of my graph. So if you notice this graph now, it's a much flatter graph, as though it's been compressed downward and flattened out. So that's the difference between a stretch and a compression. And it should become more clear as we do more examples of this. All right, let's begin with the next two types of transformations that we're talking about here: a horizontal translation and a vertical translation. The horizontal translation, again, this is maybe a little confusing because it says x minus h will shift the graph to the right h units. So that's all because the original formula has a negative in it already. So in this case, h, right, the h value, which is the x value of the vertex, will be positive. Because the subtraction is built in, it's x minus positive h, right? So h will be positive. And so positive numbers, we know, go to the right. Whereas here it's x plus h, because that simplifies to x minus negative h, right? X minus negative h. So that's minus and negative is plus. So that way h will be negative. And we know that negative numbers go to the left. All right? So again, if I have x minus 2, or I have x plus 2 inside the absolute value, we can just do a quick graph of what the parent function would look like here. And if this is right 2, so the vertex is now here, and my graph is now shifted to the right 2. Whereas if it's x plus 2, here's my parent graph. My vertex is shifted left 2. So there's my vertex. And there's my new graph, the purple one. So x minus 2 shifts to the right 2. X plus 2 shifts to the left 2. And our last one here is the vertical translations, shifting up and shifting down. And this is pretty straightforward, right? If it's positive k, it's going up. If it's minus k, it's going down. So that's pretty straightforward. It's really just the horizontals that you got to be really careful with. So this would be like x, absolute value of x plus 2. See how the plus 2 is on the outside? So that would shift it up to, there's my vertex, and we'll go from there. And if it was absolute value of x minus 2, here would be my parent function. That would get shifted down 2. So there's my vertex. And my whole graph would now be below the parent function. So those are the 4 types of transformations that you can have: reflections, vertical stretches or compressions, horizontal translations, and vertical translations. So the rest we'll just do a couple examples, and we'll practice when you get here. So let's go to the next page and look at some examples. Okay, so in this first example here, we're looking at f of x equals 2 multiplied by the absolute value of x plus 3. So let's talk about the verbal description. What's happening here? And I like to write it out as I read from left to right. So the first thing you would see is a reflection, but it's positive, so there's no reflection. The next thing is a stretch or compression. 2 is greater than 1, so this is a stretch by a factor of 2. The next thing is a horizontal shift left or right, and this is plus 3, but again that's x minus negative 3. So that is a shift left 3 units. And there's nothing happening out here, so it's kind of like it was plus 0. So no shift up or down. So that's what's happening. And what I want to do is I'm going to begin by thinking about the vertex. Remember, the vertex is the point hk. So here my h is negative 3. My k would be 0. So I can plot that here at negative 3, 0. And now again, because this is a linear, absolute values move in a linear motion, and it used to be 1 over 1, I'm now multiplying by 2. So 1 over 1 multiplied by 2 gives me a slope of 2 over 1. So from my vertex, I can go up 2 over 1, up 2 over 1, up 2 over 1. And we have our axis of symmetry here at the vertex. So I know that these points will just reflect over. And there's the graph of my function after it's been transformed. Hopefully you find that easy to understand. So right now, pause the video and try example number 2. Okay, so here's the answer to example 2. And what you should see here is that it's been reflected over the x-axis, compressed by a factor of positive 1/2. Again, your compression and your reflection are always positive because it's the absolute value of A. So this should never be negative. Then it's shifted up 3, right? My vertex is 0, 3 because inside the absolute value, I'm not adding anything. I'm adding 0. Outside is a positive 3, so that's up 3. My slope here is negative 1/2. So down 1 over 2, down 1 over 2, down 1 over 2. And we see that linear motion. We can then reflect it over, and reflect it over. And that's the graph. Next thing we're going to do here is talk about working our way backwards. So now we have an actual graph. So let's talk about what's happening. The parent function would start with the vertex here, but it looks like it's been shifted. Well, let's talk in order, right? It's not been reflected, so there's nothing to write. Here's my vertex. What does it do? That looks like a nice point. It goes up 1 over 2. So it must be compressed because it's going up less than it's going over. So compressed by a factor of 1/2. And then I see it's been shifted to the left 2. And then it looks like it's gone up 1. So when you talk about shifts, you can talk about left and right, and then up or down, and you don't have to keep writing shifted multiple times. So there's my verbal description. Then I need to write a function notation. So f of x equals 1/2 of the absolute value of x left 2, so that's minus negative 2 or plus 2, and then up 1 would be plus 1. And you should be able to write the equation if given a graph. Just like you should be able to, from the verbal description, graph it, so compressed by a factor of 1/3. Let's start with the function notation. F of x equals, compressed is 1/3, translated horizontally 3 to the right, so that's x minus 3. And then 3 units down would be minus 3 as well. So now I can talk about the vertex, which would be 3, comma, negative 3. So go over here to 3, negative 3. And then my slope seems to be up 1 over 3. There's that. Can't really go much further, but on this side, it reflects to here. And I could do it again, right? So that looks like where my graph would be on here. Okay, so those are all the different examples of how to shift, how to reflect, how to compress, how to stretch, how to look at a function's graph, how to look at its verbal description, how to look at its equation, and how to create graphs from there. If you have any questions, we will discuss them in class. and we will see you then.